All right, welcome to the Explainer. Today we're going to break down one of machine learning's most elegant algorithms, the support vector machine, or SVM for short. We're going to go on a little quest to find the perfect way to divide up data, and along the way we're going to uncover some really powerful and honestly pretty clever ideas. Okay, let's just dive right in. Take a look at this. If you had to separate these two groups, how would you do it? I mean, you could probably sketch out a dozen lines right now that get the job done. But how would you know which one is the perfect one? And that question, that's the whole key to understanding what a support vector machine is all about. So, this whole quest really kicks off with one of the most common jobs in machine learning, classification. Put simply, we just want to teach a computer how to label things, how to put them into different buckets, just like we're trying to do with these blue and orange dots.
I mean, you could draw a line here, or maybe one that's a little closer to the blue dots. You could even tilt it a bit. There are practically infinite lines that would work. But see, an SVM, it's not happy with just any old answer. It's designed from the ground up to find the one single, most confident dividing line it possibly can.
So what makes one line better than all the others? Well, an SVM has this really simple but super powerful idea called the margin, and I like to think of it as the widest road rule. So forget about just drawing a skinny little line for a second. Imagine you're a road builder and your job is to pave the widest possible road between the two groups of dots without hitting a single one. The best dividing line? It's just a yellow median strip running right down the center of that super wide road.
In machine learning talk, this whole idea is called maximizing the margin. By creating the biggest possible buffer zone, the model just becomes more robust. It's much less likely to get tripped up by new data it's never seen before, which is what we call better generalization. It's also a really clever, built-in way to keep the model from overreacting to noisy data, which is a concept called regularization.
And here's the really cool part. The only dots that actually end up mattering are the ones right on the edge of our road. These are called the support vectors, and they literally support the entire boundary. Seriously, you could delete all the other dots, and that line, it wouldn't budge an inch. The whole model is defined only by these few critical points.
Okay, that's all fine and dandy when the data is perfect, right? But let's be real, real-world data is almost never that clean. What happens when you can't pave a perfectly clear road because some of the dots are just in the way? This brings us to a really important practical tweak.
So to deal with this, we bring in something called a soft margin SVM. Think of it as having a little knob you can turn, a parameter, often called C. If you turn C down low, you're telling the model, hey, I care more about a wide road, I can live with a few mistakes. But if you crank C way up, you're saying, nope, every single mistake is a big deal, even if it means my road gets a lot narrower to avoid them. Okay, so we've got our strategy for drawing the best straight line even when the data is a bit messy. But what if no straight line on Earth can do the job?
Just look at this. The blue dots are completely trapped inside a circle of orange dots. There is no way you can draw one straight line to separate them. It's just impossible. And this is where we get to see the real magic of SVMs with something called the kernel trick.
It really is all about changing your point of view. Think about it. If you can't separate these dots when they're flat on a piece of paper, what if you could somehow lift them up into the air? Let's say you could make those blue dots kind of float up off the page. All of a sudden, separating them is a piece of cake, right? You just slide another flat sheet of paper right between the floating blue dots and the orange ones that are still on the table.
But here's the really clever bit, the part that makes this practical. An SVM doesn't actually do all the work of creating that new complex third dimension. That would be way too slow. Instead, the kernel is a mathematical shortcut. It calculates the dot-to-dot relationships as if they were in that higher dimension, but without ever doing the crazy expensive math to actually move them there. So you get all the power of that new perspective with none of the computational hangover.
All right, so we have our widest rule, and we have this awesome magic trick for when things get tangled. That's the theory. But how do we actually use this stuff on a real problem?
So that magic trick we talked about, that's what we call a kernel. And you've got to pick the right one. A linear kernel, think of that as your trusty ruler. It's fast, it's simple, and it's perfect if your data looks like you can just slice it with a straight line. The RBF kernel, that's more like one of those flexible drafting curves. It's your default choice when things get complicated and you think the dividing line needs to bend and weave.
And this right here really nails the business trade-off you have to make. The linear kernel is fast and computationally cheap.
It's your go-to for a quick baseline, especially with things like text data. The RBF kernel, on the other hand, can squeeze out more accuracy. But that power costs you in processing time. You gotta ask, is that extra bit of accuracy worth the extra compute cost?
Okay, so to really get the most out of your SVM, you have to tune it. First thing, and this is a big one, you always have to scale your features. SVMs are really sensitive to this. Then you pick your kernel, let's say we go with RBF. And finally, you run something called a grid search. It's basically a brute force way to test out a bunch of different settings for that C flexibility dial and another one called gamma, which kind of controls how much influence a single point has. You do all that, and you find the absolute perfect combo for your data.
So, with all this cool math and these clever tricks, where does the SVM actually fit in today's world? I mean, we've got all these other algorithms like random forests and huge neural networks.
Yeah, as you can see, the SVM is definitely not a silver bullet. Its real sweet spot is with smaller, medium-sized datasets, especially when you have a ton of features. Unlike logistic regression, it's kind of a black box. It's hard to explain why it made a choice. And, unlike something like a random forest, it just chokes on really big datasets, especially with those powerful curvy kernels.
So, when should you reach for an SVM? You should totally bet on it when your dataset isn't massive. Think datasets under, say, 100,000 samples, or when you have a crazy number of features compared to your samples. This happens a lot in fields like genetics. And it's great when that idea of a really clean, wide separation is key to your problem. Basically, it's a fantastic tool when you don't have the mountains of data you'd need for a deep neural network.
But on the flip side, if you're dealing with millions and millions of rows, forget it. The math for a kernel SVM just gets way too slow. You'd want to use a simple linear SVM, or maybe a neural network. And like we said, if your boss needs a clear explanation for every prediction, you're much better off with a decision tree or logistic regression.
And this quote here, it just perfectly sums up the beauty of the SVM. You see, a lot of algorithms just fall apart when you throw thousands of features at them. It's called the curse of dimensionality. But the SVM, because it's so laser-focused on that simple idea of finding the widest road, it just handles all that complexity with this amazing elegance.
You know, the biggest takeaway here isn't really about machine learning at all. The kernel trick is such a great metaphor, isn't it? It reminds us that sometimes the messiest, most tangled up problems aren't solved by just trying harder. They're solved by finding a totally new perspective that suddenly makes everything simple. So I'll just leave you with this to think about. What problem in your world right now could be solved not by more effort, but just by changing how you look at it?